we introduced the framework Meuschke that enables a comparative visual analysis of measured blood flow data in the aorta for predefined cohort settings. A predefined cohort setting comprises two cohorts, for example, healthy volunteers versus patients with a bicuspid aortic valve. After the user loads one of the predefined cohort settings, a visual overview of the comprised cohorts is shown. Here, the pre-selected features for each cohort are summarized using a histogram-based visualization. Above the histogram, the number of records that meet the selected criteria is displayed. The first number indicates how many datasets only fulfill the current attribute range, and the second number in brackets shows how many records fulfill all set value ranges. Here the user can also adapt the cohorts by adding further features, where for each feature up to 3 ranges can be defined. In order to have an overview of the fulfilling datasets, a summary shows the set attributes and value ranges for each cohort container. When the cohorts have been defined, the analysis can switch to the comparative cohort visualization view by clicking the Keep Defined Cohorts button. The user interface for displaying the global time-independent and time-dependent attributes is divided into 4 subviews. The first view provides a quantitative summary of the defined cohorts by combining statistical diagrams and values. The analysis can select 2 attributes using the drop-down menus. The distribution of both attributes is shown by a scatter plot in combination with a marginal histogram. The respective colors represent the defined cohorts. In addition, the median, mean, and standard deviation for each cohort is listed in relation to the attributes. Moreover, the scatter plot is enhanced by a colored curve visualizing the best fitting type of regression to describe the bivariate relationship between the 2 features. In addition, we created a 2D atlas to give a qualitative cohort overview. Each dataset is represented by a colored circle, where color reflects the cohort. The background color represents the density distribution of the datasets. In dark gray areas, many datasets lie close together. The lighter the background, the more dissimilar the datasets are with respect to global attributes. For the detailed exploration of the time-independent attributes, we use parallel coordinates. Each of the attributes from the pre-selected subset represents a vertical axis in the parallel coordinates, whereby the arrangement of the axes can be swapped. Each dataset is represented by a polyline in the parallel coordinates, where the lines being colored according to their cohort membership. This can lead to visual clutter, making it difficult to identify similarities and differences. Therefore, we apply the line bundling technique, which leads to a grouped representation. Since the line bundling cannot completely bypass occlusions, the order of the polylines can be changed using the colored panels on the left margin. For the visualization of the global time-dependent data, pixel plots are used that give an overview of the temporal attributes in relation to the defined cohorts. The rows represent the time-dependent features and the columns represent the measured time steps. A pixel plot is drawn for each cohort. The light to dark purple color scale shows the mean values of the attributes, while the shape represents the standard deviation. If the user moves the mouse over the pixel plot, a line plot is adjusted, which gives a detailed insight into the temporal behavior of individual attributes. Moreover, individual columns can be selected, which supports the comparison of attribute values between cohorts. Within the aorta, 6 measuring planes are defined at anatomically important positions, with each plane represented by an individual color. For the visualization of the time-independent attributes on the planes, a combination of hexagon plots and parallel coordinates is used. Each hexagon represents an attribute, where for each cohort a hexagon plot is created. Each triangle within a hexagon represents one of the 6 planes. The plane name is displayed when the user moves the mouse over the border of a triangle. Within the triangle, the mean value of the attributes is color-coded for the corresponding cohort. For a more detailed investigation of the diversity of the selected attribute, parallel coordinates can be used. The hexagon plot is used to quickly locate attributes that are very similar or different between cohorts in terms of the measuring planes. In addition, violin plots show the temporal behavior of the time-dependent attributes on the planes. Similar to hexagons, each violin plot represents a cohort, and each violin represents one attribute. Each arm of a violin corresponds to one of the 6 planes, with the color of the arm's border corresponding to the plane colors. The measured time steps are plotted along the arm from inside to outside. Dark purple-white areas represent high mean values, and thin light areas show time steps with low mean values. Similar to the time-independent attributes, physicians are interested in detecting differences between cohorts. Therefore, individual violence can be selected, while corresponding violence in other cohorts are highlighted. Moreover, the line plot adapts itself depending on which attribute and which plane corresponds to the current mouse position. To support data exploration, the user is directed to strong dissimilarities between cohorts. For this purpose, we compute a similarity measure to sort the features in the pixel, hexagon, and violin plots in descending order, starting with features that strongly differ between the defined cohorts. Moreover, we highlight temporal regions in the corresponding line plots where strong differences between cohorts occur. By activating the region-based similarity analysis, the color coding shows in which time ranges strong differences occur, where the transparency can be adapted to see the underlying data. The red line shows the currently selected time point in the plot. Other interesting characteristics are outlier. Therefore, the user can activate the automatic outlier detection in each view. This helps, for example, to study the variability of a specific feature within a cohort in more detail. To further explore interesting subgroups, the user can brush datasets in each view. Here, old healthy people were brushed in the parallel coordinates plot, which are then highlighted in the other views as well, to study their feature behavior compared to the whole cohort. All selected datasets as well as outliers are also highlighted in the depictions for the plane-based data. To export findings, small camera icons can be found in the bottom right corner of all views. When the user clicks on this icon, Gucci takes screenshots of all subviews, where another wizard opens to guide the user through the process of exporting the results. The user can add a specific title and a textual description to each image. In addition, user-specific markers can be added to the images using simple drawing interactions to highlight individual structures. Finally, the results can be saved. Thus, the user gets a compact summary of the exploration results.